Well, good morning. We left off here where we calculated the lime and the soda ash doses for stage 1. So just to reiterate, what we have is we have stage 1. Okay, so this is stage 1. Only a portion of the flow is treated through stage 1. So we bypass a portion. We treat a portion, and then we combine the two flows, and this moves into stage 2. And the reason we're doing this is to reduce the doses of chemicals. It also reduces the sludge. It reduces the capital cost because stage 1 flocculation basin is smaller than it would otherwise need to be. And we can tailor a water to the hardness level that we want. Typically, we design this system based on a magnesium concentration in our treated water. So we need to calculate the split ratio. And we defined the split ratio on Friday as the magnesium concentration in the final treated water minus the magnesium concentration in the initial, and that's the initial to level to stage coming in from stage 1, so it's the level here, divided by the magnesium concentration in the raw water minus that initial level. And typically we want a magnesium concentration of about 40 milligrams per liter in the finished water. We assume that the concentration coming from stage 1 is 10 milligrams per liter. So we're removing hardness to the practical limits in stage 1. And our initial magnesium raw concentration is 90.6. Again, all of these concentrations are in milligrams per liter as calcium carbonate. And that gives us a split ratio of 0.372. So 37% of the inflow will be bypassed. So this X here is equal to 0.372, which means that the fraction to be treated in stage 1 equals 1 minus 0.372, or 0.628. So roughly 63% of the flow would be treated through stage 1. So we need to think about now doing a mass balance, because we need to know how much hardness is entering stage 2. So all the mass balance problems that we did, okay, this is what we're going to use again, and we'll use this throughout the course. That's why we do the mass balance to begin with. So if we look at the hardness, okay, so coming from stage 1, if we treat to practical limits, the hardness from stage 1 into stage 2, so this is we're looking at this point right here. So the hardness concentration from stage 1 would be what? Retreating to practical limits. So this is going to be 40 milligrams per liter as calcium carbonate. And we have 0.628 Q. The concentration of hardness in the raw water, this was given, is 328.6 milligrams per liter as calcium carbonate. And we have 0.32. Sorry. So we have 0.372 Q. What we want to know is what is the concentration here? Q is just one, it's 1 Q. So we can write a mass balance. We have 0.628 Q times 40 plus 0.372 Q times 3 to 8.6. And that equals 1 Q times C mix. So that C mix is what enters stage 2. If we calculate this, C mix is equal to 147.4 milligrams per liter as calcium carbonate. And that is greater than the desired level that we're attempting to achieve. So we need further treatment. So remember, okay, just the split is designed to achieve 40 milligrams per liter of as calcium carbonate of magnesium 2 plus. So we've designed their split to achieve that, so we need no additional magnesium removal. And remember, if we look back at the equations, removing magnesium is more costly than removing calcium, so we will tend to focus on removing calcium if we can and leaving magnesium. What we want to do is remove the carbonate hardness due to calcium versus the non-carbonate hardness due to calcium. Soda ash is more expensive than lime, so if we can avoid adding additional soda ash, we'll attempt to do that.
Is that 40 or 10? At the bottom left there.
At the bottom, it's 40. I apologize.
Okay.
I cannot, the lines don't happen in PowerPoint if I'm not on Zoom. My guess is it's something to do with the delay in because of the internet. And I've tried to figure out what to do and how to avoid it, but I still can't figure it out. Okay. So now what we want to do is we want to do a mass balance for calcium. So we're going to do another mass balance. So we have 30 milligrams per liter as calcium carbonate entering. So 0.628 Q. We have 238 milligrams per liter as calcium carbonate. We have 0.372 Q. We have Q leaving, and we want C mix. So this previous C mix was our total hardness. Now we're just looking at carbonate hardness. And if we solve this mass balance, and C mix is equal to 107.4 milligrams per liter, which it should be, because remember we had the 40 before, and that 40 comes from the final magnesium concentration. We're not removing any magnesium in the final stage. We also need to think about the alkalinity. So we'll make an assumption that all the alkalinity is consumed in stage 1, which means we've taken that alkalinity, we've converted it to CO3, and then we precipitate it. So if all the alkalinity is consumed in stage 1, we have 0 alkalinity from stage 1. We have 198 from the raw water times 0.372 Q, and that gives us, again, now C mix, in this case is for the alkalinity, and C mix is equal to 73.7 milligrams per liter as calcium carbonate. The reason I want to do that is because I need to know how much carbonate hardness I have due to calcium. We also need to do a mass balance for CO2. We'll assume that all of the CO2 is neutralized. So all of the CO2 entering stage 1 is neutralized. So again, that's 0. Plus we had 12.5 times 0.372 Q equals C mix Q. And then that gives us 4.65 milligrams per liter as CaCO3. So what this is telling us here is this is how much CO2 we need to neutralize in reaction 1. And if you go back to reaction 1, we need lime. Okay, so that means what we will do is we need to add 4.65 milligrams per liter as calcium carbonate. We'll divide by 100, and that is 0.047 millimoles of lime to neutralize the CO2. So we need to raise that pH because we're bringing in CO2. Then for reaction 2 is our carbonate hardness due to calcium. And this here is our alkalinity. This is the carbonate hardness. This is our calcium hard. So this is our calcium concentration. This is our alkalinity. How much carbonate hardness due to calcium do I have? If I have roughly 74 milligrams per liter of alkalinity and I have 107 milligrams per liter of calcium, how much carbonate hardness due to alkalinity do I have?
Is it the 73.7?
Exactly, it's the 73.7. Okay. So that means that I have 73.7 milligrams per liter as calcium carbonate. That's my carbonate hardness due to calcium. We'll divide that by 100 milligrams per millimole, sorry. Molecular weight of calcium carbonate. And I have 0.737 millimoles of lime that I now need. So the total lime that I need in stage 2 is 0.784 millimoles. So now thinking about what do we have left? How much hardness do we have in the final water? We have 107.4 minus 73.7 equals 33.7 milligrams per liter. That's calcium carbonate. So that's the amount of calcium. This is really the calcium, the non-carbonate hardness due to calcium that we're leaving. So we're not reacting that. We also have our calcium that is due to the practical limits. And that's 30 milligrams per liter. So that's based on the fact that we have insufficient time to achieve the solubility limits. We have improper, inefficient, incomplete mixing, so we potentially short-circuiting. So we don't remove all the calcium. And then lastly, we're designing this system to leave 40 milligrams per liter of hardness in our water. And if we add this together, this is 103.7 milligrams per liter as calcium carbonate. So that's between that 80 and 120. So we're good. So the last thing we need to do is to calculate the amount of reactants. And if we look at stage 1, actually further, we have 3.011 millimoles. Stage 2, we have 0.784 millimoles. The volumes are different, so we need to look at these separately. And then for soda ash, we have 1.306 millimoles. So in stage 1, we have 3.011 millimoles or millimoles per liter times 0.628 times Q. Remember, we're bypassing a portion of the flow. 1,000 liters per cubic meter. So liters cancel, meters cubed cancel. We'll multiply by the molecular weight of calcium oxide, and typically that's what we will add is calcium oxide. And I've written this as milligrams per millimole. So millimoles cancel. And there are 10 to the 6 milligrams per kilogram, and that is equal to 4,236 kilograms per day. So it's just, lastly, we've got milligrams to cancel. So that's the amount of calcium oxide that we need per day. Nope, it's 10 to the 6 because it's milligrams. So it's 1,000 times 1,000. 1,000 milligrams per gram and 1,000 milligrams per kilogram. Okay. And then for soda ash, we have 1.306 millimoles per liter. Essentially the same calculation, except in this case we have a molecular weight of 106 milligrams per millimole, and that is equal to 3,477 kilograms per day. Okay. Now, stage 2, we're treating the entire flow. All good? And then for stage 2, we're only adding lime. And there we have 0.784 millimoles per liter. We're treating the entire flow, so the fraction is 1 times 4 times 10 to the 4 cubic meters per day times 1,000 liters per meter cubed times 56 milligrams per millimole times kilograms per 10 to the 6 milligrams, and that is equal to 1,756 kilograms per day. So the total lime is equal to 5,992 kilograms per day, and the total soda ash is 3,000, almost 3,500. Except the problem is the lime is 85% pure and the soda ash is 95% pure. And that is typically the case. So the lime that's purchased is not pure. This 106 is the molecular weight of soda ash. So that 106. So this is the molecular weight. The 56 is the molecular weight of calcium oxide, and 106 is the molecular weight of soda ash. So if this is the case, we need to take this value here, and we need to divide by 0.85. And what we're actually purchasing is about 7,050 kilograms per day of lime and almost 3,700 kilograms per day of soda ash. These are not small volumes. And which also means that the amount of sludge that we're producing is also not a small volume. So this is the final answer in terms of the amount of lime and the amount of soda ash that we would need to treat this volume of water. It's a significant amount. Any questions? I've just got a few photos to show you. We'll just look at a couple of basin types now that we've done all of the calculations for calculating our lime soda ash additions. So we've talked about paddle wheel flocculators. We can use these for flocculation. And you can see this is an open tank, and these, it's hard to see, but in here are the paddle wheel flocculators. And then you see the sedimentation basins. We also often use an upflow clarifier. If we were visiting the East Lansing plant, as we normally would do that, we would actually see these in operation. And this is a rapid mix, flocculation, and sedimentation basin all in one unit. So we have a rapid mix here. We're adding the influent, we're adding the chemicals. You can see your chemical feed here, your influent feed here. We then have a flocculation basin on this inverted cone on the inside. So this is typically a turbine type system. The water flows down through this flocculation basin and then up through the sedimentation basin. It forms what we refer to as a sludge blanket. You can actually, when you look at this, you can actually see the layer of sludge. the water flows up through here. It flows typically out over a weir and then into a channel and onto the next treatment process, which in most cases would be a filtration system. So in East Lansing, what they do is they use upflow clarifiers as the primary stage 1, and then they actually have ferric chloride to remove some turbidity because they have sludge coming in from their sludge drying pond, or sorry, water coming in from their sludge drying ponds. So they use ferric chloride, and then they have a second sedimentation system. So that's a conventional sedimentation basin, and then the water flows into filtration. Giving you some design criteria for conventional basins. These are typical. This is for softening. I'm not going to spend a lot of time on this. And then I've given you design criteria for upflow clarifiers.
Line softening process helps us remove calcium and magnesium that makes the water hard. The city has multiple wells that they pump up to the water treatment plant, and from there it enters aeration. Water cascades over metal, and this is where the actual softening of the process happens. And
How did I skip that one?
over metal statues, basically.
What I want to stop and show you here is in many cases, the CO2 levels are quite high. And as you saw that we add a significant amount of lime to neutralize the CO2, but we get no hardness removal. So essentially that's costing us money in terms of chemical addition and sludge production. Also in many cases, for instance, the East Lansing system, the MSU system, iron and manganese levels in the groundwater are quite high. And often we want to remove the iron and manganese levels in order to produce higher quality water. Now we can use an approach like MSU is using with an ion exchange system. But the system that they've chosen at MSU doesn't remove hardness. It removes iron and manganese, but it's not going to remove hardness. What this system is doing is it's aerating the water. So by aerating the water, that purges off some of that CO2. It also converts the iron 2 plus to iron 3, so from ferrous to ferric. And it converts manganese 2 to manganese 4, and both Fe3 plus and manganese 4 plus are less soluble than their reduced species. So by doing that, they can precipitate out the iron and manganese. At the same time, they can strip some of that CO2, reducing the amount of lime that they need for reaction 1. So that's what they're doing in this part of the process.
And combines with oxygen to help iron precipitate out, and it also releases hydrogen sulfide and carbon dioxide gas. The water then proceeds on to the solid contact unit, and this is where the actual softening of the process happens. And the lime is the chemical that actually helps remove calcium and magnesium as it's stirred together with the water. The water then moves on to
This is an upflow clarifier. So you can see the mixing occurring in the middle. You don't see the flocculation because it's in that inverted cone under the sedimentation basin.
carbonation. As part of the solid contact process.
This is a weir. So you can see, I drew the arrows that the water flows up. It flows up through the sedimentation basin, through that sludge blanket, and then out over a weir into a channel, and then it would move into a larger channel onto the next unit. So notice in this system, the engineer mentioned that they use recarbonation. Okay, so after softening, they're recarbonating, they're adding more CO2 in order to reduce the pH.
Filtration is done with two types of media. It's anthracite coal and sand. And the purpose of the filters is to remove particulates from the water before it's sent out to the distribution system. From there,
So we haven't talked about filtration yet, but you can see these are the filter beds here. Not the sedimentation doesn't remove sufficient amount of turbidity in order to distribute that water. So then the water has to then flow through a filtration basin. You can see the empty one next to it. And basically what it's doing is it's flowing through sand, and we remove that additional turbidity in the sand filter.
the water, once it's filtered, heads on to the clear well. It's fed with some chlorine to help disinfect it before it leaves the plant so that the water stays safe to drink in the distribution.
So any questions about this? It's just a short, I'm just going to play this short portion of the video. You can watch the rest of it later so that you get a better sense. You know, you can look at the whole system, but I wanted you to get a better sense of the system. I've got one other tour we can quick do. And this is Plainfield Township, Plainfield Township's treatment plant.
This is water from 11 wells located in 2 separate well fields around the area. These wells have the capacity to pump more than 19 million gallons of water per day into our treatment plant, where the water is then treated to meet or exceed federal and state requirements for safe, clean drinking water for more than 40,000 residents and neighbors. When the water first enters the plant, chemicals that help keep our bodies safe are carefully measured and added. Aluminum sulfate helps to remove particles, while fluoride prevents cavities, and chlorine guards against bacteria. The water is then softened. Using lime from the UP, the water heats by chemical reaction and creates a milky-looking slurry that's super.
So I mentioned that they add lime. Same thing in this system here. They're adding calcium oxide. What they need to do is they mix that with water. It actually creates a significant amount of heat in that reaction. It's an exothermic reaction. And then that slurry is then what's pumped into the reactor. So that's what was pumped into your rapid mix basin, either in an upflow clarifier or in a conventional rapid mix basin. So you take calcium oxide, react it with water to produce calcium hydroxide.
Saturates the water. The mixture causes heavy particles like calcium and magnesium to sink to the bottom, while the softened water goes to the filters. The filters consist of bell-shaped tubes that contain layers of a semi-permeable substance, including gravel, fine sand from Iowa, and anthracite coal. After the water is run through the filtration system, the water is...
So notice that filter, they give you a cross-section, so you have a sense of gravel at the bottom, that's basically your support, and then you have sand. They actually, in this system, have anthracite coal. We'll talk about that much later in the semester, but basically what they're doing is they're using the anthracite coal to sorb or attach to soluble organic material. So the anthracite coal is really not a filtration process. It's a sorption process or an adsorption process where the organic chemicals are attaching onto the surfaces of the anthracite coal and they're removed that way versus a physical separation in a filter.
Pumped into one of our on-site storage reservoirs, where it stays until being repumped to one of our 14 storage tanks, and then on to customers. We typically keep an average of 14 million gallons in storage before it is shipped through more than 300 miles of pipes that distribute water to homes in Plainfield.
So notice here, they talk about 300 miles of pipe. That's not unusual. This is for a township. City of Flint, for instance, had over 700 miles of pipe. We need to make sure that the water that we distribute, not only it meets all the regulations at the plant tap, but we need to make sure that it meets all of the regulations at each one of these homes that you see in the photo. So what we need to do is we need to make sure that the water is what we call stabilized. That means that what we don't want is we don't want the water itself to be dissolving the pipe. We don't want lead leaching out of plumbing fixtures, service line materials. We don't want iron leaching from dissolving from the pipes. So the last thing we'll look at with lime soda ash softening, we'll do this on Wednesday, is how do we ensure that we have what we call a stable water so that we're not dissolving, releasing metals from the piping network. So we'll stop there. Happy to answer any questions.
Professor,
Yes.
could you go back to the example problem really quick?
Sure.
Just like the end of it? Okay, so can you kind of explain like what's going on with all the conversions and stuff? It's a lot, and I kind of got lost.
Okay, it's a lot of conversions, I understand. So we start with the amount of lime, and let's just look at it first with this is lime. So we calculated the amount, the molar amount, or moles per liter. We're multiplying, this is the fraction that we're treating. This is Q. This is just a conversion because we have liters here and meters cubed here. So we need this. This is the molecular weight of calcium oxide. And this is just a conversion because we have milligrams here and we want the answer. We were asked for the answer in kilograms per day. I could have asked for milligrams per day, but I asked for it in kilograms per day.
Okay, so the 3.011 is the total line that we need just in stage 1?
Correct. And that we calculated on Friday. So this was the amount of lime that we calculated for stage 1. This is the amount of soda ash that we calculated for stage 1.
Okay, so then we left those alone for a while and came back and brought them back in for this final part.
Correct.
Okay. Also, the first thing that we started with that split ratio, can you go to that again? I missed what a couple of them stood for. Like the MGI is like the initial. I got that. What's the F and the R?
So the F is the finished water. So typically we design the split ratio so that we have about 40 milligrams per liter of magnesium in our finished water. And that's based on experience, knowing that at about 40 milligrams per liter, the water isn't going to taste kind of a metallic taste because of your metal, isn't going to scale or produce significant scale in the distribution system in your water heater. So that's where that 40 comes from. The magnesium, the R is the raw magnesium. So if we went back to the original statement, that was the magnesium concentration in the raw water.
Oh, okay. So we already given that.
Yeah, that we're given that in at the beginning.
Okay, thank you.
Okay, no problem.